Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm pleased to welcome Radha Regina from Cornell. I'm sure most of you know him. He started out doing parallelism sort of work and worked his way over into analysis and pointers, and now he's been sucked into pointer analysis big time, doing shape analysis. And supposedly he's going to tell us how to do it efficiently.
Okay, thank you. So this work is a joint work with Brian Hackett, and who was here an intern last summer, and this summer as well. He worked with Manuvir, and probably other people here know him as well. So the goal of the work that I'm going to tell you about today is the detection of memory errors for programs that manipulate linked structures. And the emphasis here is on heap structures, and especially recursive heap structures. Now, the memory errors that I'm talking about here are the standard ones, things like memory leaks or unsafe memory accesses, double freeze, and so on. What we want is to detect errors statically, to use sound analysis techniques as much as we can, and to develop solutions that are practical. Okay. Now, in general, when it comes to analyzing pointers and pointer-based structures, there are two general techniques here. These are pointer analysis and shape analysis. Pointer analysis aims at detecting May-points to relations between variables in the program, and there are a number of algorithms that have been developed over the past decades, including scalable analysis, and actually a number of people here at Microsoft have worked on this problem. However, for the problem that we're interested here, detecting, for instance, memory leaks and unsafe accesses in recursive structures, pointer analysis is too imprecise. Shape analysis, on the other hand, is essentially an accurate analysis of heap structures, and it has been fairly successful at analyzing heap structures, recursive heap structures, and finding or verifying that such errors do not occur in heap manipulating programs. However, shape analysis are fairly expensive, and they usually targeted the verification using shape analysis targeted programs on the order of tens of lines of code, or at most hundreds of lines of code. So what I'm going to try to argue about today is that if you combine these two analyses, then you may get the best of both worlds. In other words, you may get a system that is both efficient and precise. Of course, the question here is how you put together these two pieces, how you put together shape analysis with pointer analysis. And it turns out that when we started working on this problem and we tried to combine the two, we actually ended up with a new algorithm and a new approach for shape analysis. So here's what I'm going to talk about today. I'm going to talk about this new shape analysis algorithm, and there are two key ideas here that I want to convey. One is that we build a shape analysis on top of a pointer analysis, thus moving part of the complexity and the burden in shape analysis down to the more scalable pointer analysis. And second, the shape analysis algorithm that I'm going to talk about is such that it reasons about one single heap location at a time, as opposed to reasoning about the entire heap. And I'm going to claim that this approach leads to analysis that are more efficient and makes it possible to build interprocedural analysis and incremental analysis. In the second part of the talk, I'm going to show you how to apply this shape analysis technology to the problem of detecting memory errors. And I'm going to talk about an implementation that targets C programs and is aimed at detecting memory leaks and unsafe memory accesses, and tell you a little bit about our current experience with this implementation. Now, before I go and tell you what the algorithm is, let me quickly give you a brief overview of shape analysis. So the goal in shape analysis is to statically extract or verify invariants about heap structures. And examples include invariants about aliasing or about reachability or even sorting invariants. Actually, a fundamental invariant in shape analysis is that of unsharing, and this is shown on this slide here. This invariant essentially captures the notion that all the elements in a heap structure have a reference count of at most one. They have at most one incoming reference. Okay? And this allows the compiler to distinguish between a tree structure and an arbitrary graph, for instance. A tree structure has the root with no incoming references from the heap, and all the other cells in the structure have exactly one incoming reference. It also allows you to distinguish between cyclic structure and acyclic structures. Actually, the intuition behind this invariant, why is this invariant so powerful, is that it essentially expresses unaliasing. If you take a structure that has this property and you dereference a location in the structure, what you're going to get is a cell that is unaliased with respect to all the other cells in the structure. And this is why this invariant is actually so powerful. Now, why is it difficult to check that a program or a data structure maintains such an invariant? Well, there are two reasons. One is that in the presence of recursive structures, the compiler has to reason about an unbounded number of heap cells. And second, in the presence of destructive updates, these invariants are temporarily invalidated. So the goal of the analysis is to determine that these invariants are being restored as the destructive operations finish. Okay? So let me give you a quick example here. If I have this swap procedure that takes a list and swaps the first two elements in the list, you can see that you start with an acyclic list here, and you end up with a list structure here. Okay? However, it turns out that somewhere in the middle of this computation, you have a structure that is not a list, actually. This structure here looks more like two lists that have a shared tail. And at a closer inspection here, you see that there is one cell in particular that has two incoming references. And this is what invalidates the invariant that I talked about in the previous slide. So you can see that although the invariant holds at the beginning and at the end of this procedure, it is temporarily invalidated. Now, the lesson that we learned from here is that shape analysis is inherently a flow analysis. You need to do a flow-sensitive analysis over this code to determine that the invariant is being restored. And this is somewhat bad news because in the pointer analysis world, the scalable analysis are those that are flow insensitive. So flow insensitivity is where you gain a lot of efficiency and scalability. For shape analysis, you have to do a flow analysis. Okay. So how do a general shape analysis work? Well, they use this flow analysis, an abstract interpretation, or a data flow analysis. And essentially what you have to do is come up with an abstraction of your memory and then define how the program operates on that abstraction. Given an abstraction and the program statement here, x next equal t, what is the abstraction that you get after this statement? Okay, so this is how all shape analysis work. Now, what is the abstraction? There have been various proposals. The most common ones are shape graphs, which encode the memory using finite graph abstraction, or three-valued logic, where you encode this information. Essentially, you encode the shape graphs using three-valued logic structures. Okay. Now, let me look at the scalability side of shape analysis. Well, although shape analysis, as I said, has been very successful at verifying very complex heap properties, it has had limited success at working well for larger realistic programs. And in particular, interprocedural shape analysis is a difficult problem. The reason here is that you have to propagate this sophisticated, complex abstraction across procedure boundaries. And if you look at the shape analysis algorithms that have been proposed, actually few of them have an interprocedural component, and only a subset of those have been actually implemented. And those that have been implemented turned out to be somewhat expensive. So what I want to argue in this talk is that the reason for this is that abstractions here are monolithic. They describe the entire heap. Okay, and because of that, it is difficult for the analysis to keep track of this big abstraction, to propagate them across procedures, and this is one of the reasons for lack of scalability. So in this context, here's what we propose. So what I want here is take this whole memory abstraction and essentially break it down into smaller pieces so that the analysis can reason in a modular fashion about the pieces independently. Okay? And we decompose this in two ways. First, we break it down into a shape analysis that is built on top of a pointer analysis. Okay? Here, the pointer analysis is going to give an abstraction of the program consisting of a set of disjoint regions and points to relations between these regions. Okay? And essentially, what this does is that it frees the shape analysis of the burden of reasoning about aliasing in unrelated structures. It's going to make the shape analysis just reason about aliasing within the same recursive structure. And this is actually what we want. And there are a number of pointer analyses that have been proposed. We are not tied to a specific pointer analysis. Any of those can fit into this bottom part here. Now, the second thing that we want to do is break down the granularity of shape analysis itself. What we want to do is break this heap abstraction into smaller pieces. And key here is that we want these pieces to be independent such that the analysis can reason locally about each of them without any knowledge about the other pieces in this abstraction. Okay? Now, although the sum of all these pieces collectively describes the entire heap, however, these pieces are independent and we can reason about them locally. Now, what are these pieces that I'm talking about here? Well, if I take one piece like this and I zoom in, well, we call each of these pieces a configuration. And the key part here is that each of these talks just about one single heap location, which we refer to as the track location. So each of these pieces is a description of one heap cell. And it has no knowledge about any of the other location. It has no knowledge about any of the other parts of the heap. Okay? Now, let me make this a little more concrete and tell you what exactly is the information that we capture about this individual location in here. So the information that I want that we currently have in this configurations for the track location are the following. We keep track of references from each of the regions in the program, and these regions are provided by the underlying pointer analysis. And then we keep track of two things here, heat expressions and miss expressions. Heat expressions are some program expressions that reference the current track location. And miss expressions are expressions that are known to point to a location that is different than the track location. Okay? So this is the general idea of how we want to build this heap abstraction. Now let me show you a concrete example. Now let me take this concrete memory and show you how we build the abstraction for it. So this is a list with 5 elements. I have 2 variables, x and y, that point to the first 2 elements in this structure. So the abstraction that we build for this concrete memory has 2 components: the underlying shape abstraction, the underlying points to abstraction, and the shape abstraction. The region abstraction given by the pointer analysis in this example consists of 3 regions, one capital X, another one capital Y for the 2 variables X and Y. So these ones model X models the location of variable X, and region Y models the location of variable Y. And then there is a third region that models the entire list here. Okay? And of course we have many points to relations between these regions. So this is the points to abstraction here. But this abstraction doesn't really tell me that X points to the first element and that Y points to the next one, or that X and Y point to consecutive elements in the structure, and so on. So this is missing from this points to abstraction. Now this is going to show up in the shape abstraction. So here's how we build this shape abstraction. Let me take the first element in this list here. And I'm going to use this configuration to describe it. So this configuration consists of reference counts, heat expressions, and miss expressions. This is the triple that I'm going to use to describe this location. Reference count, I indicate the region, and with a superscript, the reference count from that region. So in this case, I have a reference count of 1 from region X. The second component here shows that X is a heat expression. And the last one says that I don't have any information about miss expressions in this program. Okay.
What's a miss again?
A miss expression is an expression that is known not to reference the current location.
So why Y in there?
So this is a possible abstraction. You can use richer sets of misexpressions in here, but they are not actually needed in
So for this concrete example, Y could be the set containing Y could be a potential candidate.
That could be a potential candidate. You don't really need it because you already know that you don't have incoming references from region Y. So what the analysis does, it tries to minimize the sets of hit and miss expressions to keep just what it needs to compute the final result. But yes, these expressions could be richer expressions.
But in the region abstraction, you don't know. Actually, Y could point to the first thing.
So in the region abstraction, these three represent disjoint pieces of memory. So if I say here that X has this location has an incoming reference just from X, it means that it has zero incoming references from all the other regions. So So if I include here Y, that would be redundant information.
Yeah, okay, I see. Okay.
Yes.
So is there some kind of may versus must thing on the hit and miss? Because otherwise it's
hit and miss
together to the whole program.
The hit and miss expressions are actually must relations. They must hit or they must not hit. Yes, this is actually, that's a good observation, as opposed to these relations here, which are all may relations.
But how different is this from ESP in some sense? That the first component is the state of the finite state machine in some sense, and the next two components is the VA, the value alias set.
So this component here talks about the recursive structure. As far as I know, ESP doesn't have support for describing recursive structures and talking about individual locations in the recursive structures.
But anyway, you are checking just one location, starting from one track location, and figure out what that set.
Yes, except that now, as I said before, recursive structures have an unbounded number, a statically unbounded number of heap locations, so we don't know exactly how many there are, and this just talks about one of those. Okay? Yes.
A question about the reference count. So does that have to be conservative? That it has to capture all regions that could possibly reference this?
This has to be precise. So all this information is most information. So when I say X1 here, I know for sure that there is exactly one reference count for that region. It's not 0 or 1.
So
exactly one. And all the ones that I haven't shown here are 0.
Okay. So that's what I was asking. Yeah. So,
yes.
So it has to be over approximating
all the other
references.
It's not over approximating. It's exactly describing the reference.
I think it's
suppose there's some
you had
region
something
Z
that had
somewhere.
two things coming in. How
Suppose there's some region Z there, okay, as well.
Yes.
Then, if it could possibly reference this first element, then it would have to appear in that list.
Yes. Actually, I'm just going to show an example of that as well. And this example is this one here. So if you look at the second element here, it has an incoming reference from region Y and an incoming reference from the next pointer, the first cell in here. So here I said that there's a reference count of 1 from region L, the reference count from region Y. The set of hit expressions here are Y, but also the next field, X next here, saying that actually I'm pointing just to the next element after X. Okay? And again, I use an empty set of miss expressions here. So this configuration describes the second element in the list. Third element in the list, well, I just have an incoming reference from region L. I don't have any, let's say I don't have any known hit expressions. And however, I know that X next here doesn't hit the location. It says that this is not the second, the element right after X. Okay? And actually, this describes any of the last 3 cells here. So this abstraction here models any of those 3 locations there. However, it is not a summary node as in other shape analysis. It doesn't describe the set of these locations. It just describes one of these locations. So as far as the compiler and the analysis is concerned, here I have just one location, not a set of locations. So this is what the abstraction of this concrete memory is in our compiler. And the key thing here is that these 3 components here are independent. When I'm talking about the first element in the list, I don't know what's the structure of the list at the tail. Okay? When I'm talking about the second element, I don't know what's going on with the first element or with the remaining elements, and so on. Now, if I want to model a cyclic list like this, then actually the only thing that I have to do is add one more configuration here that describes the cell that has two incoming references, and I'm going to describe that with an L2 here, and again, X next in the miss set. So in other words, these three configurations here describe, if you want, the non-cyclic portion of the list, all the parts of the list that have a reference count of 1 or 0, and this one describes just the cell that introduces the cycling here. And this is the result that I get here. Yes?
So in the third row on the right side, why did we not have X arrow, N arrow, N as a hit expression?
So the hit and miss expressions are program expressions. If X arrow, N arrow, N is an expression that that occurs in the program, that you can put it in here. So this abstraction here is one possible expression. It's not it's one possible abstraction in here. Okay.
And then can you say that we can look at this as a shape analysis in which you are going to track all the predicates that talk about program expressions?
So I'm going to show you how you do shape analysis right after this. Okay. Yes.
Can you ever capture directed acyclic graph?
Directed acyclic graphs. Well, we can capture in the sense that we have this allocation. If you have a DAG, then there is a cell that has multiple incoming references and is going to show up as a reference, as a configuration with more than one references to it.
But you cannot distinguish from just the usual graph, right?
So you can distinguish between that if you add more information, things like reachability information. But this is pretty much as powerful as the shape graphs this captures the same kind of properties as the shape graphs. The shape graphs cannot distinguish between the DAGs and the cyclic graphs either. The cyclic graphs either.
The one thing that I don't quite see here that I know in the shape graphs is I don't see how you. Suppose I had my Y pointer there pointing to one of these cells, then I actually get to the next one using X to N.
So that's what I'm going to show
Can I
you
talk
right
about
now.
that? I sort of don't see the inductive part of the.
Exactly. I'm going to show you how that works. So, given this abstraction, how does the analysis work, and how the analysis extracts this kind of information? And I'm going to do that by example. I'm going to use the standard example that is being used in shape analysis literature, an in-place list reversal. I have here a list X that I receive as parameter. I reverse the list and return the reversed list in here. The shape analysis problem here is the following. Given an acyclic list X at the input here, is the return list here acyclic as well? Okay. So here's how this works in our framework. Well, first of all, this procedure here has, well, the parameter X and two other variables T and Y. So the region abstraction is going to actually use a region for each of these three variables, X, Y, and T, and then it's going to use a region for all the list elements. And we're going to model the acyclic list at the input using just two configurations. The first one with a reference from X essentially is the list head, and the one with a reference from L is any of the elements in the tail. Okay? So let me take the first configuration here and look at the loop body. These are the four statements in the loop body for reverse. And let me show you how the analysis reasons about this location. So all I know is I have a heap location that is referenced from this region X, has heap expression X, and I know nothing about miss expressions. Okay? So here's how the analysis works. It reasons about this, the first statement here as follows. It looks at the two sides of these assignments, and it tries to detect what regions they correspond to. Well, X is a variable in region X. Following the next pointer, according to the points to graph, I get something in region L. Okay? Y, T here is a location in region T. Well, I have two things that I'm assigning, two references that I'm assigning, and one is in L, the other one is in T. My incoming reference is just from region X. So essentially, this says that this statement doesn't have anything to do with my current location. So it just leaves this location, the state of this location unchanged. So I get the same thing after the statement. And you can use a similar reasoning for the next assignment in here. However, at the third one, things change a little bit. Now I look at the right side of this assignment. I see X is a heap expression, so it references this location. Y is in region Y. I don't have references from Y, so it misses the location. So I'm writing a reference to the location in some region that used to have no references to this track location. So what I have to do is add a reference from region Y, and also add Y to the set of heat expressions here. At the next statement, pretty much the opposite goes on here. I take something that doesn't reference the track location, and I write a location that used to point to that location. So I'm essentially removing a reference, and this is what happens here. I remove the reference X to this location. So this is what I get about the reasoning of this individual location here. Yes?
So you didn't put T into the miss location on the previous slide?
Yes.
And how do you know at the last line?
It's not because, as I said, when Tom asked that question before, I have that information from the reference found here. T is in region T. I know that I have no references from region T, so I can put it in here. It's going to be just redundant information. The reason why I put it in the heat expressions is that sometimes I group multiple variables in the same region, and I have to distinguish which one is the one that hits the track location. So this is the result that I get. Now, let me look at the concrete state of the heap. So let's say I run this reversed procedure with a list of 4 elements, and I look at the second iteration of the loop here. Okay? Now, what the analysis computed here actually is exactly the state of the location that was originally pointed to by X. For instance, at this point, it determines exactly that this location is pointed to by X and Y. Here, it determines that it's pointed to exactly by Y. So essentially, what we did here is we analyzed what happens just with this location out of the entire heap. Okay. Now let me look at the other configuration that I had for my acyclic list at the input. The other configuration looked like this. It says that I have a location that is pointed to by an X pointer. It's not pointed to by X and Y, and I have no knowledge about hit and miss expressions. So the reasoning here is going to get a little more complicated, and that's why I want to show you this example. Now, what's going on here is, well, T here, we know that it's in region T, and it definitely doesn't hit the location. However, X next here is in region L. And we know that we have an incoming reference from L. We just don't know which one that is, okay? Because we don't have any information in the heat expressions here. So what do we do here? Well, what the analysis does, it bifurcates. It says, okay, I'm going to look at each of the 2 possibilities. Either X next hits this location, or it doesn't hit this location. In either case, I add it either to the set of heat expressions or to the set of miss expressions. If it hits the location, then I'm creating one more reference from T here. If it misses it, then the state remains unchanged. However, I learned that on this side here, X next misses the expressions, misses the location. Okay? Yes?
So I'm a little scared because I see one side where it basically says, oh, it must have this other pointer coming in, and I see one for it must not have this other pointer coming in. But is there some perturbation of the program where we have to model the fact that we don't know whether there's something?
So that's exactly why we have a bifurcation here. That's exactly what we had here. We
okay, so
know
you don't have to
concretely
say it because you've enumerated the possibilities.
Yes, we enumerate the possibilities, and we analyze them in cases where we precisely know if that's the case or not.
Sure.
It's similar to the index values in ESP, where you don't want to merge that information. Here, I don't want to merge that kind of information, and I want to keep it separate whether it hits or not. So actually, this example shows exactly why these hit and miss expressions are useful in this kind of analysis. If I look at the next statement, I see that X next is being written here. Okay, and I know in each of these 2 cases if X next points to the track location or not. In this case in the left, I know that it hits the location, so I know that this is going to write this location with something that doesn't reference the location, so I can remove this reference from L in here. And I'm going to end up just with the location with a reference from T. And this is because we know have information about x next in the set of heat expressions. In the other case here, I know that x next doesn't hit the location, so essentially none of these two sides of the assignment have anything to do with my location. It just leaves the state unchanged, and this is what I get. Okay? So here it was very important to know what happens, what's the relation between x next and my location that I'm talking about here. And you can complete this reasoning, and you're going to get something that looks like this in this example. Of course, this is the loop body, so you need a fixed point computation. For instance, here you end up with a configuration T1x1. You have to propagate that at the top of the loop body and continue the computation. And what you're going to get at the end is something that looks like this for the whole reverse procedure. Okay? These boxes represent configurations, and I just omitted the hit and miss expressions for readability. Now, the nice thing about this is that the rows in this structure actually are entire heap abstractions. For instance, if I take this highlighted row here, this shows me what is the state of the heap at this program point before y equals x. Okay? However, I could reason about each of these pieces separately without knowing anything about the other pieces. So this is the key part in this analysis. I can also look at the first row and the last row, and I actually can see that the first row says that I started with an acyclic list where I don't have reference counts of 2, and I end up with an acyclic list in Y that doesn't have reference counts of 2 either. So I essentially verified this property. Now let me also go into the case where we have a cyclic input to this reverse function. And I want to go through that because actually that gives some very interesting insight about why this approach works. So let me say I fit into reverse a list that has a cycle, probably because of an error in the program. What's going to happen with reverse? Is it going to crash? Is it going to leave memory? What is it going to do? So we want to find out what's the behavior of reverse for this malformed input. Now, it turns out that it's not immediately obvious what reverse does here. You may think that it's going to loop forever because of that backhatch in there. Actually, it does terminate. And the way it works is that it goes through the list and reverses all the pointers along the way, and when it hits the back pointer, it comes back and fixes the pointers at the beginning of the list. So the result of reverse is actually something like the original list, but with the reverse cycle in there. Okay? And this is a result that you get for reverse. Now, what does the analysis say for this example here? Well, here's what the analysis say. Well, if you start with a list that has a cycle, and that is represented by these two configurations that describe the non-cyclic part of the list, plus one that corresponds to the location that causes the cycle here, then what you're going to end up here is a structure that has a cycle. Now, the interesting part about that shows up here is not that we get a cyclic structure if we start with a cyclic structure, but the interesting part is that the cell that caused the cycle in the input structure is exactly the one that causes the cycle in the output structure. And this is what gives the insight about this reasoning about individual locations in here. And indeed, we can reuse all the analysis that we did for the acyclic case, and this is shown in this part here, where I start with these configurations and I get these other ones here. And then I can separately reason about this location that is highlighted here in yellow. And that is going to say, well, if I have a region that has a reference count of 2 here, that is going to cause the cycle in the output structure as well. Okay? And you can see that with other examples as well. For instance, if you have shared lists, so if you take the reverse procedure that I showed you before, and you slightly change it so that it takes list y as a parameter, and essentially it reverses list x and prepends it to list y, and you fit in a structure that represents 2 lists with a shared tail. Again, there is a cell there that has a reference count of 2. Well, the result of prepend here, again, it's not immediately obvious. You have to go by hand through this example to figure out what it does. But it's going to end up with something that reverses the shared tail and makes a cycle out of the list at the beginning. Okay? And in particular, we have exactly the same behavior. The cell here that caused the structure to be shared is exactly the same that has a reference count of 2 in the output. So this is why these two examples actually give this intuition about why this reasoning about individual locations actually work. Okay, now let me stop here with examples and talk about the analysis algorithm at a more general level. So, so I'm going to tell you how this works in the general case. Yes?
So do you let the reference counts to be symbolic values, or they have to be concrete, 1, 2, and 3?
They are concrete values. In the implementation, actually, in practice, we've seen that it's good enough to have a very low value of k equals 2 for those references. The analysis just so we bound this value to make the abstraction finite, and we bound it to actually 2. So we haven't seen cases where we needed to keep track of more than 3 references. But I have to emphasize here that this is 2 references per region. So you can have more references as long as they come from different regions. Okay? But they are concrete values. They are numeric values of 0, 1, 2, and so on. Okay, so what is the general algorithm? Well, we have 2 phases, a points-to-analysis phase and a shape analysis that builds on top of that, as I said before. In the current implementation, we use a flow-insensitive but context-sensitive analysis. And here we use context sensitivity because we really want to distinguish between unrelated structures that are allocated at the same site. So this is the reason why we currently use context-sensitive analysis. The shape analysis, well, it has both an intra- and inter-procedural component. It is flow-sensitive and context-sensitive. And the key part here is that the whole analysis, both the intra- and the inter-procedural analysis, works at the granularity of these individual locations, at the granularity of configurations. So let me tell you more about the shape analysis. The intra-procedural part, well, what you have to do to build this analysis, you have to look at what happens with mallocs and what happens with assignments. Mallocs essentially inject new configurations in the code. And whenever you see a malloc, you inject a new configuration that describes the newly created cell. And that is fairly straightforward. For the analysis of statements, what you want is, given the state of your track location before the assignment, what is the set of possible states that you can get after the assignment? And the way this works is similar to what I've seen with what I showed you in the examples. The analysis looks at both the sides of this assignment at E1 and E2 and tries to determine whether they hit or not the track location. And we use a small decision procedure based on all the information that we have in the configuration to decide this kind of fact. And if that decision procedure fails, and we've seen an example in the previous slide, then we bifurcate the analysis. We bifurcate it in 2 cases where we precisely know whether it hits or not the track location. And we proceed by analyzing these precise cases. So what happens in each of these cases? Well, you have to do 2 things. Well, you have to update reference counts, and you have to check what are the new hit and miss expressions in there. Updating reference counts is fairly easy. Usually you only have to increment counts, decrement counts, or leave them unchanged. The more difficult part is actually updating that hit and miss expressions. And just to give you a flavor of what's going on here, consider this example here. Let's say that I have an expression E that is a miss expression, and I execute this statement E1 equals E2, and I want to determine if E still misses the location. Well, we use a reasoning along the following lines. Well, either the R value of E is unaffected, that means E represents has the same value as before, in which case we can keep E in the set of miss expressions. Or the L value of E is unchanged, but the value that we are writing in here is a miss expression. And the intuition behind this is that we have 2 cases. Either E2, the value that we write it exactly in E, in which case it would not hit the expression, or it does not write that, so the value of E is unchanged, but it didn't hit the expression before either, so we still can keep it in there. So this is the kind of reasoning that we use in here to keep track of this. So it's a little more involved. But again, you can think of this as a small logic engine that reasons about what's going on with this individual location. And then if you want to put the whole algorithm together, you build a data flow, a standard work list algorithm. However, this work list algorithm works at the granularity of individual configurations, not entirely with abstractions. And on the theoretical side, we have proved that this, we have formally proved that this algorithm is sound with respect to the semantics of the underlying language. Now, what happens at the interprocedural level? Here we have a context-sensitive analysis. And the idea is that we have this context expressed in terms of configurations. Essentially, if I have one configuration that describes one location before a function, then what is the set of locations that correspond to this one at the end of the function? This is the relation that we capture during the interprocedural analysis. And if you think of the graph structure that I showed you as the result for reverse, you can think of the output configurations being the one that are reachable from the input configurations that you are concerned with. So it's more a graph reachability problem in that sense. However, you don't really need to keep track of that graph. What we actually do is we tag location, we tag configurations with the configuration that they originated from, and this makes it easier to determine for a given input what are the outputs, or for a given output what is the input that they originated from. Okay. There's also the analysis also involves changing the analysis domains when you go from one procedure to another, but I'm not going to go into those details here. Instead, what I want to say is that the fact that we work at this small granularity of individual location is what really buys us a lot. If suppose that you have analyzed a certain call site, and then you run into an invocation of the same function at a different site, and you have a different abstraction of the heap. Well, what you can do is take each of these pieces and see if you have analyzed them before. So here you're doing a matching granularity of individual locations, not entire heaps. So matching is much easier here. Moreover, this works also if you have just partial redundancy. So assume that I have a call site where I have here 5 locations on the left, and I run into another a call site that have 4 locations. And let's say that I manage to map 3 of them, these ones shown here in yellow, with ones from the previous site. What I can do is reuse all this work that I did before and just analyze the function for this new location that I got here. So for instance, think of reverse. I analyze the function for an acyclic list for the 2 input configurations, and I run now into a call site with a cyclic list. Well, I have to analyze just the additional L2 configuration that I have in there. Or even better, if I first analyze the cyclic case, then I already have the results for the acyclic case. Okay? And this is the key part that makes it work well with interprocedural analysis. Yes?
How do you know how to do the match? You're using the region information to get together collections of things on the formal and actual side that you combine together? Or how do I know that it's that? Because the locations have... So I build some correspondence between what happens outside and inside the procedure, right?
Yes. So as I said before, there's a process, a mapping process that where you go from the analysis domain of the caller to the analysis domain of the callee. So we first do the mapping and then do the matching of configurations. So when we do the matching, we have the same scope, the same analysis domain. Yes.
Do you have a logical characterization of what this abstraction is? I mean, it seems to me the closest thing is sort of the separation logic, where they actually have this idea of this disjunctive heap abstraction, right? And do you have some feeling for what sort of logic it corresponds to?
We haven't looked precisely at this problem. It's unclear how this precisely relates to separation logic. Well, separation logic is a logic, so it allows you to prove things, but it requires the user to provide you the proof. Here, we want a model where you can synthesize this.
No, I'm just thinking, so very often an abstract domain has some logic associated with it, and I just wonder if there is some strong relation between this and separation logic.
We haven't
seems quite a different abstraction than shape analysis and the canonical abstraction.
So the thing here is that only the shape component is actually close to the separation logic. The underlying pointer analysis is actually more a global abstraction, and it talks about the entire memory. So somehow we move the global reasoning down to the pointer analysis, and just the shape analysis corresponds to the separation logic, where we talk about completely independent structures. So it's a combination of global information in the points to analysis and local information that is similar to the separation logic in here. But we haven't looked at the precise logic that this corresponds to. Yeah.
So do you have a sort of an equivalent to a frame axiom? Is when I call a method at a call site, I have a lot of locations and configurations that are not affected at all by the procedure that I'm calling.
Yes.
Right? And I'm going to just carry those over. So suppose you have this linked list thing again, right? I may have other pointers outside from locations into this linked list, but those are never touched by the linked list reversal.
Yes.
For example, how does that affect your matching and your analysis?
So during this mapping process, we exclude the things, the locations that are not reachable from the callee,
So
and we just propagate this.
Reference counts, for example, as well, right?
Yes.
Okay.
So we just propagate that information. We distinguish between the locations that may be affected by the callee and the ones that are not reachable and therefore not affected by the callee, and we just propagate those directly. And something similar happens when you return from the function back. All the locations that are local to the invoked procedure are not going to be propagated back.
Sort of effect.
Yes, and that is part of propagation across different procedure domains, which I said. And we can talk more offline if you want to.
Question about the representation in the the misset and the headset of expressions. You said the expressions are actual expressions in the program.
Yes.
They must appear in the program, or
yes, we have that.
Constructed new expressions.
We require that to keep the abstractions finite, because otherwise you have an unbounded number of possible expressions.
But that could be problematic if you in this into when you match the formal and an actual argument. Like something is x arrow n, and then when you pass to a parameter.
And you check it whether you have an expression in the invoked function that matches to your expression. Otherwise, you just use empty sets. Okay, let me move on. So not only this approach makes it easier to build interprocedural analysis, but it also it works well with on-demand and incremental analysis. For instance, let's suppose that you want to figure out what happens with a structure allocated at just one particular site. But what you have to do is just inject a configuration just at that site and not at any of the other sites, and keep track, trace this particular location throughout the program, from the allocation point up to the functions that enclose these allocation points, and so on, up to the allocation point, or even further, even after it has been deallocated. Okay? And the result is going to characterize just what happens with a structure allocated at this site. And even better, if you want to analyze other allocation site later, then you can add those later. And what the benefit that you get is, because you work at the granularity of individual locations, then you're going to be able to reuse previous work, both at the intraprocedural level with this kind of matching that I showed you before, and at the intraprocedural level in the work list algorithm as well. Okay. Now, let me move to the second part here and talk about error detection. So far I showed you how you do a shape analysis. It may not be entirely clear how this maps to the problem of error detection. So it turns out that this is fairly easy in our framework. Suppose that you have a language that supports explicit deallocation. You have a statement that frees a certain expression in there. So the only thing that you have to do is essentially add one bit into the configuration, this bit here, that tells you whether the location has been freed or not. And this is pretty much all you have to do to apply this technique to the problem of memory error detection. Whenever you have a malloc, you set this bit to true. Whenever you have a free, you set this bit to false. And you keep tracking this location even after the allocation point, so that if later on you dereference this location, you're going to catch that.
So is the bit always concrete? So do you have to split if you don't know?
Yes, exactly. So we keep the bit in the index, and we keep a precise value of whether it's true or not. And that's because we want to apply this both to leak detection and unsafe errors. In one case, you need to know if it definitely, if it may be deallocated. In the other case, you want to know if it may not be deallocated. So if you want to check for unsafe accesses, let's say I see a star E in my program, there are two things that I check. Does E, is there a possibility for E to reference the track location? And second, is the track location being deallocated? If both of these are true, then I warn these as a potential memory errors. Double frees fall pretty much in the same category if you check a free as a standard dereferencing here. For memory leaks, well, I check if the track location has no reference count from any of the regions and if it has not been deallocated yet. And in that case, that means I don't have access to this location. However, as you mentioned before, it may be the case that you don't have references in the current function, but you have references in the closing functions. And that's why we do check these things only at the end of the function that actually allocated this location, the track location. That's when we perform this check. Of course, this has the standard problem associated with reference counting, that it does not detect leak cycles. However, we believe that this can be addressed by including more information, things like reachability information in the configurations. Now, let me tell you a little bit about the implementation and the results that we had using these techniques. So we implemented this combined shape analysis and pointer analysis into an error detection tool using the Swift infrastructure. We targeted C programs, and we want to detect memory leaks and unsafe memory accesses via dangling pointers. And this is a sound analysis. Actually, to be more precise, shape analysis is guaranteed to be sound as long as the underlying points to analysis is sound. However, the pointer analysis uses standard assumptions, things like pointer arithmetic doesn't violate the structure bounds or the array bounds, and so on. And we we looked at two classes of programs here. First, we looked at some standard list manipulation algorithms, and then we looked at a few larger programs. So, about list manipulations, well, first we looked at manipulations of singly linked lists. And this approach worked well for all the algorithms that we looked at: insertion, deletion, reversal, and so on. However, we found that the analysis is somewhat sensitive to the way programs are written, and these two code fragments here give you an idea of why that is. So these two pieces of code here are exactly the same. The only difference is that here I have x next, here I have t next. But they are the same because these two variables are identical before this assignment. Well, it turns out that this one works with our analysis because the analysis places t next here in the hit or miss set and then uses this information at the next statement. Here, it cannot do that because it doesn't know at this point, it doesn't record the fact that if x next hits the location, that also t next hits the location. Of course, what is missing here is information about variable equality or expression equality, and we believe that these can be added into our framework. When we looked at doubly linked lists, actually, it turns out that the current analysis doesn't work for this kind of programs. And the idea here is that currently the information that we keep in the configurations is too local and doesn't capture the notion of local structural invariants. Again, we believe that these can be added on top of our current framework, and we can capture these things in the configurations with more complex algorithms. Now, let me tell you a little bit about the programs that we looked at. We looked at three programs, SSH and fragments of SSL, of the library SSL, and of the BNutil Unix utilities. And the results are as follows. We pretty much looked at about 70K lines of code. The analysis for all 3 programs took less than 2 minutes. We reported about 100 errors, and about 40 of them were actual errors in the program. Now, these results are pretty promising, especially if we notice that this is actually more scalable than previous shape analysis. To the best of our knowledge, previous shape analysis have been used only of programs up to 3K lines of code. So what we have analyzed here is pretty much 1 order of magnitude larger than that. And to give you a more concrete example here, recent work in interprocedural shape analysis using TVLA shows that although this analysis is quite precise, well, it takes some recursive version of delete or insert. It takes it more than the time that it takes us to analyze all of these applications together. So we have actually, this gives us confidence that our approach actually leads to efficient implementations. Now let me tell you a little more about these tests and the errors and false positives that we got in these applications. So first of all, the testing strategy that we used here was the incremental approach. We looked at each allocation site 1 by 1, and we analyzed them separately. Of course, we used this incremental approach in the sense that we reused the previous analysis results whenever we added 1 more location. The errors that we found, well, all of them were memory leaks. We didn't find any unsafe reference via dangling pointers. In many cases, these were caused because the program would not deallocate data structures on abnormal return paths from the procedure. For instance, the connection in SSH would fail, and instead of deallocating the procedure, you just return. Okay, so this is not that the program terminates, it's just that the procedure abnormally terminates. Of course, there were also a few cases where the data was actually never freed on all paths, all return paths from the procedure. As for the false positives, we have a few warnings about unsafe accesses, but as I said before, none of them were real errors. The cause for imprecision that led to these false positives was, well, there were many causes. These included lack of path sensitivity information. Sometimes the state of the track location was dependent on some error code in the program, and we didn't capture that. Also, we've seen cases where the imprecision in pointer analysis triggered false warnings in here as well. Yes?
Can you actually check for null pointer dereferences?
Currently, we don't do that, but that we think that can be added and extended in this framework. We only track locations. Okay, we could probably check for null dereferences if we regard each null in your program as a track location.
Right, but you only have regions that point to a region. You only have reference counts. You don't have the regions which a particularly
but you don't need that.
Points to.
You can just model as a special location, right?
Yes, each null occurrence in your program, model it as a location. And then the whole thing works just as I showed so far. Now, the problem with doubly linked list that I mentioned before showed up here. And actually, what happens is when the programs traverse this doubly linked list with multiple pointers, what we ended up with is an exponential blow up in the number of configurations. Essentially, it took the analysis to a halt, and it didn't terminate. But because we used this incremental strategy, we were able to separate these cases from all the other cases and just present the results for all the cases that we have successfully analyzed. These cases, the cases where we had doubly linked structure, were about 10% of the allocation size that we have looked at. Actually, 10% in the case of SSL and BNUTLs. We have analyzed all of them in SSH. Yes?
So could you say more about how the blow-up really materialized in terms of how the configurations look?
Yes, so the blow-up occurs because if you have, let's say, 3 variables, x, y, and z, you get all combination of possible references from these locations. So you have n factorial here.
So in the region reference count?
Yes. Yes, because the reference counts are essentially the index values in this analysis, so we keep them separate always. we don't merge. If I have x1, y1, and x1, z1, we don't merge them. However, despite this fact, I think that these results are pretty good. They yield a ratio of errors to false positives of 60%, 66%, which is pretty good for analysis that uses sound techniques. Now, let me also tell you a little bit about some strategies that we used for debugging here. We found it quite useful to keep track of error traces. Whenever we encounter an error, we actually print out the cause from the allocation site to the point where that caused the errors. And this makes it quite easy to determine what was the cause and inspect what was the bug in there. So this was a very useful thing for debugging. Also, what we did is error clustering. In some cases, the errors, we get multiple errors that essentially refer to the same problem in the program. So we clustered these error traces that we got above based on what is the point that they originated from, and reported just one for each cluster. Now, what we've seen is that actually most clusters have just one trace. This was the common case. A few clusters have 2 or 3 errors. Even some of them had 7 or 8 traces in there. And there was one cluster that was very big, had more than 100 traces. They were all referring to the same thing. This was actually caused about the imprecision in pointer analysis, which merged together 3 different structures, 3 different global structures, and that confused the shape analysis. Okay. Now, let me tell you a little bit about where we want to go from here. Before I end this talk. So first thing is to address the limitations that I mentioned so far in here. And we believe that most of this can be added in the current framework of reasoning about heap locations using local reasoning. And we envision that this is going to translate into something that looks like this. For instance, the robustness issue, the fact that programs are sensitive to the way they are written, I think that can be addressed by using an underlying analysis that tells our shape analysis whether different expressions are the same or not, and then use that information in the logic about the track location. About path sensitivity, we can add more information in these configurations that capture information about the path that is taken in the program. Structural invariants, we can add this information in here. Say, for instance, that starting from the track location, if I follow next and then previous, then I get back to the track location. And keep track of this invariant. And finally, for a leak cycle, you can add reachability information here and detect whether or not a structure is actually leaked or if it's just a leaked cycle. Okay. Now, of course, all this is going to make all this information, all these configurations bigger, and accordingly, the logic that is associated with this is going to be bigger. But on the other hand, the trade-off is that you're going to have fewer spurious configurations, so the overall running time may actually be better. Other directions, well, somebody already mentioned this, null pointer dereferences. You can also add this to track uninitialized data. You can extend this to track not only heap data but also variables on the stack. But more interesting is to see how this framework extends to multi-threading and multi-threaded programs. How can you extend this to detect errors in multi-threaded programs? Things like data races or leak of certain resources, for instance, leaking logs in a program. And finally, one interesting direction is to see what's the to investigate the relation between the underlying pointer analysis and the shape analysis. How much does the pointer analysis affect the shape analysis? How much does the efficiency of the underlying pointer analysis affect the efficiency and the precision of the shape analysis that is built on top? Okay, and that is again something that we want to look at and evaluate. So here's some related work in the area of shape analysis. As I said before, there were a number of many algorithms that have been proposed. Most important are the ones that are based on shape graphs, and more recently the ones on three-valued logic. There's also work in interprocedural shape analysis using three-valued logic. And probably related here is the notion of heterogeneous abstractions, where essentially the abstraction models precisely just one part of the heap and has an imprecise view of the rest of the heap. However, this approach still models the entire heap, although it does that with different degrees of precision, as opposed to our approach where we model separate parts of the heap. So our abstraction is homogeneous but has a different granularity. As for error detection tools, there are a number of such tools. Many of them have been developed here. And these include tools based on model checking or on user annotations. Also, there are some tools like metal and prefix that use unsound analysis techniques. Our approach is probably closer in spirit to ESP and the Clouseau tool developed at Stanford. The difference is that, well, in ESP, you don't focus towards recursive structures, and this is exactly what our focus is here. So it's pretty much complementary to ESP. And with respect to this other tool, Clouseau, that is aimed at detecting memory leaks in C and C++ programs, the difference here is that our approach is more general in the sense that it doesn't target just memory leaks, but it can also handle other kinds of errors like unsaved references. This tool here is concerned just with the memory leak problem, and it cannot actually be applied to the problem of detecting unsafe memory accesses. Okay, let me conclude here, and I'll be happy to take any questions you may have. Yes?
So you said your abstraction is parameterized by the number of reference counts from each region. Let's say it's 2. And so what is the complexity of the interprocedural shape analysis for this constant 2?
So the complexity, well, actually it showed up in one of the actual tests that we performed with real programs. As other shape analysis, this can lead to an exponential blow-up in the number of possible configurations. So if I have n regions in my program, then I can have at least n factorial possible configurations in there.
Okay, and how about interprocedural?
How about interprocedural? That's exactly the same. It's still exponential in the same. It's exponential in theory, just because the structure of the call graph leads to an exponential blow-up in the number of possible call sites that you have to analyze. Now, it just depends on how many of them can you reuse previous work, and this has been actually seen in pointer analysis as well, where the theoretical complexity is exponential, but using this caching technique, you can have actually running times that are closer to linear in practice or polynomial. So theoretical, it's both of them are exponential.
Can you give some idea of the properties that you miss on since you consider only individual locations and you do shape analysis on individual locations, or what you call as local reasoning?
Why I call this local reasoning?
So what are the kind of properties that you miss on because of doing
the local properties are exactly the ones that require more information than just one single location. So for instance, to give you an example, if you want to reason about balancing of trees, you need to reason about subtrees as well. So you have to go in a larger area around your track location to capture this kind of property. You cannot reason just about this, but also about the children.
So let's not talk about more sophisticated properties, but for simple properties like null pointer difference, or
yes.
So did you figure out that there were any false positives because of your local reasoning?
Yes, well, so the example with doubly linked list is an example of that. We didn't have enough information in the current cell to capture this local invariant, and that's why we weren't able to analyze precisely that case.
Another way to maybe think about it is in terms of shape analysis. I mean, the thing that really to me characterizes it is not so much the use of three-valued logic, but the use of transitive closure in order to essentially deal with reference counting, but in a very powerful way. And so it seems like with the power of transitive closure, there are certain things you can say about global heap structures. A collective, you can talk about the set of cells reachable from X. Whereas here you have some ability to do something like transitive closure, but
a limited form of that.
In a very limited form, right?
It just depends on how much information you encode in this.
In the configuration.
Yes.
Right. I mean, you can power up the configuration to start to tell you more about the region around you, but it's still somewhat local. I mean, like with transitive closure, you can locally sort of talk about something arbitrarily formed.
Well, in the worst case, you can encode the whole shape graph in one configuration.
Sure.
So you can go to that extreme.
I mean, this is actually exactly the reason why shape analysis isn't modular, because
it's because it goes out, and this is exactly what we're trying to do.
But that's another way to sort of understand it. I mean, once you sort of put transitive closure in your logic. So that's why I'm also interested in thinking about what is the logic sort of underlying this, because it probably doesn't have transitive closure, but you're able to do certain things like, with the reference counting.
So I think the logic is related to the actual information in the configuration. So if you add more, probably you move to different logics in there.
So my case is that I think you're doing abstract interpretation over predicates. So given a region configuration, so now TVLA essentially asks you for a set of predicates from a user. Now you're having some kind of implicit predicates, and your predicates are equivalences between program expressions and which are your hit expressions. Mixed expressions are disequivalences, things that are known to be definitely not equal. And then you have this reference counts also. And if you limit the number of the reference counts, then the only predicates that you're taking is the reference count 1 and is the reference count 2. And now you're doing an abstract interpretation on let's say conjunctions and disjunctions of such.
That is true. So that is true, but however, you have to keep in mind that this builds on the pointer analysis, where you essentially express a global property. So when you go into the region abstraction, that is actually a global property. It gives you the whole entire points to graph. So this kind of limitation that you have is just in the region part of the in the shape part of the abstraction. But yes, this is exactly what all you can express, just this reference count and this information about heat and mix expressions.